Okay, so this is 14.6a, or day 1, video number 2. So we've defined now what the directional derivative is. And basically it is a slope in the direction of any unit vector. So it doesn't have to be with respect to the x or y axis. However, these two obvious cases should cover that. So if we want to find the directional derivative, I'm going to go ahead and write the formula for that over here again. The directional derivative in the direction of some unit vector at a point x naught, y naught is the limit as h approaches 0 of f of x naught plus ha, y naught plus hb, and that kind of came from that question mark thing I did on the previous page, minus f of x naught, y naught over h. So case number 1. What if we let our unit vector be the vector 1, 0? Well, since we've defined the unit vector to be AB, that means that A is 1 and B is 0. So let's fill it in. We would take the limit as h approaches 0 of f of x naught plus h times 1, h times a. A is 1, so that's plus h, comma, y naught plus h times b. But b here is 0, so that's really plus nothing. Minus f of x naught, y naught, all over h. And hopefully what you should see here is that the y naughts, or the y sub zeros, are constant. They're not changing. The only thing that's changing here is the x's. So what is this? This is really nothing more than the partial derivative with respect to x at x naught, y naught. And that should make sense. The unit vector is a vector 1, 0. That is a vector in the direction of the x-axis. So likewise, and you should probably have figured this part out too, case 2, whoops, put my colon in the wrong spot above, but oh well, would be if the unit vector is the vector 0, 1. Then you would have the limit as h approaches 0 of f of x naught plus h times 0, which is nothing, y naught plus h times 1, so plus h, minus f of x naught, y naught, all over h. And again, what you should see here is this time the x's are staying constant, but the y is changing. So that is just the partial of y at x naught, y naught. So again, those should make sense because that second unit vector is in the direction of the y-axis. So how do we do this? How do we actually go about doing one of these problems if it's not one of those obvious cases? So we have to start with the fact that we're trying to find a directional derivative at a certain point in the direction of some random unit vector. Okay, so what we have is g is going to be defined, so g of h is going to be defined as f of xy. So in this case, because of the way that's defined, g is our dependent variable. G is dependent. X and y here are going to be our intermediate variables. X and y are intermediate variables, and that's going to be where your point is, and h is going to be independent. So if I wanted to find the derivative of g with respect to h, because I probably should have mentioned this, that h right here is a function of x and y, And really, that's going to end up giving us our slope here. So to find the slope of g, sorry, I'm having a hard time with my eraser here. I'm not even going to write it that way. So h is a function of x and y. That's all we really need to say there. So if I want to find dg dh, those are full derivatives because there's only one independent variable. It's going to be the partial of g with respect to x times the full of x with respect to h plus the partial of g with respect to y times the full of y with respect to h. So now what is all this stuff? So that's going to be your directional derivative of f of xy. dg over dx is nothing more than the partial of x at some point, x naught, y naught, and then dx over dh is just a. The derivative of x with respect to h is a. I'll show you where that comes from in just a second, if you don't remember. And then the dg dy is fy at x naught, y naught. And then the derivative of y with respect to h is b. Now, where does that come from? All the way back up here. The derivative of x with respect to h is a. The derivative of y with respect to h is b. So that's where these two things come from. So I'm going to go ahead and just draw like little lines. That, oops, did not mean to use that line. That's that piece. That's that one. That's that one. And there's your b. So this is how we find a directional derivative. You're going to take a partial of x at your point times a plus the partial of y at your point times b. Okay, and we're actually going to go ahead and define that as something else. If you take the directional derivative in that form, this is what is called the gradient. So the directional derivative is given as, okay, I'm going to go ahead and write it back here again just so we have it. A partial of y at x naught, y naught times b. I'm sorry, if I said it was your gradient, I apologize. You're using the gradient to find the directional derivative. We're about ready to define the gradient. So what you can see is, or at least hopefully you can see, is that if I use the vector f sub x at x naught, y naught, f sub y at x naught, y naught, and I dot that with the vector AB, I get the step above. Well, this piece right here, which is just your partials, the vector that's created by your partials, is what is called the gradient. Gradient. That's the gradient vector. Also notated by this kind of weird looking upside down triangle. That is known as the gradient. If you see that, that means find the gradient. And all the gradient is, once again, is the partial of x and the partial of y vector. That's it. That's what the gradient is. And then this piece over here, that's your unit vector. We've already defined that. So the gradient is just the partials. As soon as I dot it with the unit vector AB, it becomes the directional derivative. That's it. So now let's actually see how easy this stuff is to do. We're going to probably fly through most of these, I would think. All right, so given f of xy equals the function there, the point is 1, 2, and the unit vector is given to us, which is nice. find the gradient of f, find the gradient at p, and then find the directional derivative. So the gradient is the vector of the partials. So all I have to do is take the partials of these. So on part A, the partial of f with respect to x is going to be 5y squared minus 12x squared y. Oops. Yeah, that was right. Oh, I forgot my comma. Sorry. Nope, that is wrong. I don't know what I am thinking right now. I'm not thinking. It's too late. That's the partial with respect to x. The partial with respect to y is 10xy minus 4x cubed. That's the gradient. Gradient of f. Now I want the gradient at the point P. So part B says I want to take the gradient at, we were given the point 1, 2. Well, that just means take 1 and 2, plug them in for x and y. So let's see what we get there. If I plug 1 in for the x's, that's not going to do much. Plugging 2 in, so 2 squared is 4 times 5 is 20. Minus 24, so it looks like we're going to get minus 4. And then let's see, in the second one, 10 times 1 times 2 is 20. Minus 4 times 1 cubed is 4, so that's going to should be 16. So I think we're going to get negative 4, 16 for our gradient at that specific point. And then we want the directional derivative. And the directional derivative at the point 1, 2 is going to be the gradient vector dotted with the unit vector. And we are going to get, what are we going to get? Negative 20 over 13. Ooh, 16 times 12. 16 times 10 is 160 plus 24, no, plus 32 more is 192 over 13. So adding those two things together, we're going to get 172 over 13. And what this is the slope at the point 1, 2. So whatever the surface of this thing looks like, it's the slope at the point 1, 2 in the direction of that specific unit vector. Not in the direction of the x or the y axis, but in that specific direction of the unit vector. So think of it this way. You're standing on the side of a mountain somewhere, and a mountain obviously doesn't just have an x and a y axis, but it certainly does have a slope. And it's got a slope in every possible direction. As you rotate yourself 360 degrees standing in that one point, you can see a different slope in every possible direction. In some ways, it's going to go more sideways. In some ways, it's going to go more steeply up. In some ways, it's going to go more steeply down. There is no way to specifically define your x and y axis. And if you did, that's fine. But everything in between there is also going to have slopes. That's what's called the gradient or the directional derivative. And if you've ever been driving on mountains or whatever, and you happen to see like those yellow signs that says 12% grade ahead, that's where it comes from. It's about the grade. It's about the steepness, the slope of the road or whatever. All right, so we're given in number 2, g of st equals s squared e to the t. The point we're given is 2, 0, and we are given the vector I plus j that we want this thing to be in the direction of. The problem is I plus j is not a unit vector. Okay, so we have to start off with the fact that the vector is the vector 1, 1. We want it to be a unit vector. So in order to make a vector a unit vector, we need to divide it by its magnitude. So let's find the magnitude of v, which is the square root of 1 plus 1, or the square root of 2. And then we're going to divide, or basically we're going to multiply everything by 1 over root 2. So you're going to get the unit vector to be 1 over root 2, 1 over root 2. So if you're not already given a unit vector, you have to take whatever the vector is for the direction and create a unit vector. All right, so now we want to find the gradient. So we need to find the gradient vector. All right, so the first thing we do is take the derivative with respect to s, because that was the first variable here. So that'll be 2s e to the t. Then we take the derivative with respect to t, which is going to be s squared e to the t. We want that specifically at the point 2, 0. So we need the gradient. I put f up here, it should be g. Put the gradient of g, at the point 2, 0. So plugging in a 2 for s and a 0 for t. So that's going to be 2 times 2, which is 4. E to the 0 is 1, so we get 4. S squared is going to be 2 squared, which is 4. E to the 0 is 1, so once again we get 4. So now if I want the directional derivative at the point 2, 0, it's going to be the gradient 4, 4, dotted with our unit vector 1 over root 2, 1 over root 2. So we're going to get 4 over root 2 plus 4 over root 2, which is 8 over root 2. And obviously you can simplify that. You can rationalize it if you want to and simplify it, but this is perfectly fine. So we basically have a slope of 8 over root 2 in the direction of the vector I plus j, or 1, 1, which is a 45-degree angle in between the x and y axis in this case. All right, number 3. So this time it specifically lays out for us again. So we want to find the gradient of f. Gradient of f. And this time we have x, y, and z. So we've got a 3-dimensional gradient here. So our gradient with respect to, the partial with respect to x is going to be e to the 2yz. E to the 2yz. With respect to y, remember x and z are constants here, so it's really just going to be the derivative of that exponential. So it's going to be 2z x e to the 2yz. And then with respect to z, it's going to be 2y x e to the 2yz. Yeah, that looks right. And then the gradient at our point, 3, 0, 2. Just make sure we do all this right. Make sure I do it all right, that's for sure. So if I plug in y and z, well, y is 0, so it's going to be e to the 0, which is 1. Once again, the e part's going to be 1 because I'm still going to have a y up there. I'm going to have a y in all of these actually. So every one of these e parts is just going to go to 1 because it's going to be e to the 0. So then it's going to be 2 times z times x, which is going to be 2 times 3, which is 6 times 2 is 12. And then in the last one, I also have a y on the outside, so that whole thing is 0. So there's my gradient of f. I need to have a unit vector. And if you haven't already checked, that actually is a unit vector. And you would know because if you square all the pieces, add them together, and then take the square root, it's going to be 1. So that is a unit vector up there. So for part C, because I should have labeled these up, part A, part B, part C, the derivative, directional derivative in the direction of our unit vector, which was nice. And by the way, they labeled it U, so we know it is a unit vector. It's going to be 1, 12, 0, dotted with 2/3, negative 2/3, 1/3. So we're going to get 2/3 minus 24/3 plus 0. So that should be negative 22/3. So we have a negative 22/3 slope. Okay, again, not really difficult to do. Just be careful on your partials and plugging numbers in, and hopefully you're not doing this too late at night like I am. All right, so let's do the same thing here. We've got our partials for our gradient. All right, so I have to do the little bit of a chain rule type of thing here. So if we were to take the partial, I'm going to do this off to the side. It's going to be 1/2 the whole thing on the inside to the negative 1/2 power times 2 times whichever variable it is. So for like, if I do this with respect to x, it'll be 2x because the other pieces were constant. These 2's are going to cancel out, which basically means you're going to have whatever variable you're taking this with respect to on top, and the whole thing in here is the square root, but on the bottom. Well, the square root itself is f. That's the function. So I don't know if you can see this or not, but really what we're going to get is x over f for our first partial. It'll be y over f for the second partial, and then z over f for the third partial. If you cannot see that, please, by all means, just write them all out. It's not that big of a deal to do. We are going to need to find the gradient at the point, what is the point? 1, 2, negative 2? 1, 2, negative 2. So if we find what this thing is at 1, 2, negative 2, that'll be nice because that'll be all of our denominators. So let's see, if I plug in 1, that's 1 squared, 2 squared is 4, another 4. So we get the square root of 9, which is nice. That's 3. That makes our denominator 3. And then we're going to have x, y, and then z on top. Now this vector over here, it's a vector v, does not look like it's a unit vector. We need to create a unit vector. So let's see, what's the magnitude of v going to be? So 6 squared is 36, another 36 is 72, and 9 is 81. So the square root of 81 is 9. That's really nice. So the magnitude is going to be 9, which means that my unit vector is going to be negative 6 over 9, or negative 2/3, positive 2/3, and negative 1/3. So for part C, we want the directional derivative at the point 1, 2, negative 2. So we're going to have 1/3 dotted with 1/3, 2/3, negative 2/3, dotted with negative 2/3, 2/3, negative 1/3. So what are we going to get here? Negative 2/9 plus 4/9 plus 2/9. The 2/9 are going to cancel out. Looks like we get 4/9. So that's your slope. All right, I think we've got one more to do. Let's see. Yeah, one more. We'll finish it off. It'll be a slightly more lengthy video, but again, these are not difficult to do. It's a good amount of practice problems. Biggest thing with this one is we've got some polar. We got some trig going on here because I got an angle of negative pi/6. I do have to. I think I have to add a point here. I didn't give us a point. So let's say this is going to be at the point 4, 1. There we go. Okay. Well, we can take our gradient. We can find the gradient. The gradient of f is going to be 1/2 the whole thing in here. Probably could have used the same trick I did last time to the negative. No, I can't. To the negative 1/2 times the derivative of the x part, which is 5, and then 1/2 times the whole thing in here to the negative 1/2 times the derivative of the y part, which is negative 4. Yeah, okay, so now we need, well, I guess we could simplify this a little bit. So the 5 is going to go on top. This part right here is our original f function, just put into the denominator. So I'm going to get 5 over 2f. And over here, we're going to get negative 4 over 2f technically, but I'm going to reduce that to negative 2 over f. That might be easier to deal with. I don't know. Maybe it wasn't. We'll see. Okay, so now we need the gradient at the point 4, 1. So plugging 4 and 1 back into here because we're going to need to find out what f is. So plug a 4 in, we're going to get 20 minus 4 is 16. Square root of 16 is 4. So really this one's going to be 5 over 2 times 4, which is 8. This is going to be negative 2 over 4, which I guess I could have reduced to negative 1/2. So that'll be 5/8 negative 1/2. So there's our gradient at our point. Biggest thing is, what is our unit vector going to be? They didn't really give that to me. They gave it to me in polar. Well, if theta equals negative pi 6, I can create a unit vector that has to do with angles. And the easiest unit vector to create is going to be cosine theta, sine theta. And how do I know that that's a unit vector? Well, square each component, cosine squared plus sine squared, add them together, you get 1, take the square root, you still get 1. It's probably the easiest one to use. And we know that x is cosine theta and y is sine theta, which is why I put them in that specific spot. So there is a unit vector. So we can do the directional derivative at the point 4, 1 is going to be 5/8 negative 1/2. Now I do need to evaluate my unit vector at negative pi 6. Oops, that shouldn't be equal. It should be dotted with. So if I plug in negative pi 6, see, cosine of negative pi 6 is going to be, that's in the 4th quadrant, so it's root 3 over 2. Sine of negative pi 6 is going to be negative 1/2. So I'm going to dot that with root 3 over 2, negative 1/2. And finishing this thing off, we are going to get 5 root 3 over 16 plus 1/4. And you can simplify it if you want to get a common denominator, but that's it. All right, very long video. I apologize for the length of this. I don't think any of this stuff is too hard. I think you should probably be okay with this section.